The idea of an area function, which we'll call a of x, is something that's used in detail later in the course when we get to the end of Calc 1 and we're looking at something called the integral. We use this area function quite often as a way to talk about the area under a curve, or essentially between the curve and an x-axis. So let's start with the definition. The area function, which we'll call a of x, is the area under the curve to the right of the y-axis. So let's just do a quick sketch to get an idea of what this means. So say we had some arbitrary function, maybe like that. We'll call that f of x. Then what the area function is for some arbitrary x, let's call it that, is essentially you would draw a line up like that, and it's this area in here under the function. So by that we mean between the function and the x-axis, but to the right of the y-axis. So then this business here is a of x. And when we get to integrals, we'll expand this idea a little bit. We'll relax it so we don't have to have it be to the right of the y-axis. And we'll talk about what it means when the curve goes under the x-axis. So there's a long way to go here. We're just getting our feet wet with this idea. But notice that we could move this x to the left and to the right, and the area under the curve would go up and down depending upon how we moved it. So that's essentially what the area function is. Let's look at an example where we can actually compute the area function for a few different values of x. This example says if f of x equals 3, find the following, and then it asks us to find a of 3, a of 10, and a of x. So for these kinds of examples, you want to graph the function first and then use geometry to compute these area functions. Once we get into integration at the end of the course, we won't need to graph them first. You can use all kinds of analytical techniques, but for now we're just going to graph it and use old-fashioned geometry to find these areas. Well, f of x equals 3 is a horizontal line that goes through the value y equals 3. So that's a nice way to start studying these functions. And remember, we're only looking at the area under that line and above the x-axis and to the right of the y-axis. So let's see here. So for a of 3, all right, so we're going to look at here 3. So we'll use that to essentially make a box, right? So there's 3, so we'll trace that up to the function itself, and then it's this area in here. And then if you recall, the area of a rectangle is area equals, I guess, length times width. So let's see here. The width here is 3. The height is 3. So a of 3 is 3 times 3, which is 9. It's just the area of that square, in this case. For B and C, it'll be rectangles. Let's look at a of 10. Okay, so now we're going all the way out to 10. That's over here somewhere. So it's going to make a nice rectangle, something like this. And we're looking at this whole area. Okay, so the area is length times width. Let's call the length the vertical distance. So that'll be 3 times the width, which will be 10 in this case. So we have 30 units. Now for part C, we want a very general area function. We want just a of x so that we can quickly plug in any value and we don't have to keep worrying about these rectangles and all that. So let's just define some arbitrary x here. I'll do it between 5 and 6, totally arbitrary, but no matter where we put it, it still makes a rectangle here, and the area will be, let's see, length. Well, length is still 3, we're defining that as the height, times the width, which in this case is x. So let's just rewrite that as 3x, and there you go. So now that we have a well-defined area function, we could put in any number we want and very quickly get the area out without having to use the rectangles anymore. Let's try a slightly more involved example. Here we have if f of x equals x over 3, find the following, and then asks us to find a of 3, a of 6, and a of x. So again, let's start by graphing that function. It may be a little hard to recognize what this is, but we can think of this as y equals 1/3 x, and technically it's plus 0 because there's no y-intercept there, but we essentially leave that off. But in case you're searching for a y-intercept, there is none.
Okay, so it's just 1/3 x, so we start at the origin. That means we go up 1 over 3. There we go, up 1 over 3. Okay, let's look at a of 3. So for a of 3, that means we want this area up to 3 to the right of the y-axis and under the curve, but above the x-axis. So we're essentially looking for this area of this triangle here. And we need to recall the area of a triangle. Let's see, area of a triangle, thinking back to geometry, 1/2 base times height. Remember that formula? So for a of 3, we have a base of 3 and a height of 1. So it's 1/2 base times 3 times height is 1. So a of 3 is 3/2. Not so bad if you can remember the area of a triangle. Let's try a of 6. Okay, so now we're going all the way out to 6. More triangles. Much of calculus is actually, well, rectangles and triangles can really get you pretty far. It doesn't use a ton of really complicated geometry. Okay, so there's our triangle. So we have 1/2. Base is 6 times height. Well, now the height is 2 there. Okay, so what is that? 12 over 2, which is 6. Okay, well, we can imagine this geometry approach would get cumbersome after a while. So let's come up with a general equation for a of x. Okay, so now I'll just pick some generic x, maybe out here between 7 and 8. It could be anywhere. Okay. Interesting. So we know that the base is x, and the height is whatever the function is evaluated at that x. So I'll say the height is f of x. But f of x is x over 3, so it's simply x over 3 is the height. So whatever you put in for x, x over 3 is the height. So the area is then 1/2 times the base, x, times x over 3 for the height. So here's our base, here's our height. Well, that simplifies nicely into 1/6 x squared. Now that we have the formula, we could ditch the graph completely and just use the formula. For instance, what if we wanted to use the formula to find a of 3 now instead of the graph? So we plug it in, we have 1/6 times 3 squared. Well, that's 9/6, which simplifies down to 3/2. Same thing as we had before. Now we can do it without using the graph. So that's a little preview of much of what the second half of the course does for us. It takes something that we initially need geometry for, and then we decide that the geometry is a little bit too cumbersome, so we come up with a formula to then find the area analytically. That's a grotesque oversimplification, but it gives us an idea of where we're headed.